Howdy, I'm Philip Loy. I am the team lead for SureFire engineering group, and our project is the thermocouple and flow rate transducer test benches. My role on the team as team lead has been mostly management side of things, so ensuring deliverables are on time, acting as a liaison between our group, the Navistar engineering team that is overseeing this project, as well as the two ECE teams that we are working with on this project. So project summary for this is Navistar is a leading manufacturer of diesel engines, semi-trucks, and school buses, and they have a research and development center here in San Antonio, and their thermal management validation team has tasked us with producing two test benches, one being the thermocouple test bench and one being the flow rate transducer test bench. We are working in cooperation with two ECE teams, one ECE team being assigned to each test bench. The purposes for this project, for the thermocouple test bench, they use a lot of thermocouples, up to 150 per test in the facilities that they use. So there's a lot of cycling between thermocouples and need to ensure that the thermocouples are working correctly between tests. So their current method of testing and calibrating their thermocouples is extremely inefficient and takes hours at a time to complete the testing cycle for just one thermocouple. So with this system, the thermocouple test bench that we're designing, we plan on being able to test many thermocouples at one time and significantly reduce the cycle time to test the thermocouples. And similar story for the flow rate transducer test bench. They need to be able to test their flow rate transducers between tests that they're performing on their facility. So this bench is to be able to test a single flow rate transducer at a time, not necessarily to calibrate, but just to ensure that it's functioning properly. They still will need to send all of these sensors off to a metrology lab to do official calibration for government work and everything. But these are just to ensure that things are working in between tests and in between the times that they send them out to a metrology lab.
Hi, my name is Hugh Nguyen, and I am the thermosystems engineer for the thermocouple project. And my contribution to this project is the engineering analysis to the system. So the purpose of the thermocouple test bench that we designed is to make it more efficient. The one currently at Navistar, they can only test one thermocouple at a time, and it's all done manually. And the overall objective is to decrease the time and make things more efficient. So with the engineering analysis, our test bench is going to be able to test up to 16 thermocouples at the same time, and all of it is going to be done hands off. It should be automatic. It'll take less than 5 minutes to do. So for the engineering analysis, I calculated for the silicon oil and for the actual outside convection. There's two types. One convection for the actual oil, and then one convection for the actual inner casing. And there was heat loss that was calculated due to that. So for the additional design, we've decided to include additional installation for inside the case and between outside of the bath and inside the actual case. So that'll prevent any kind of injuries or burns. So it's just a safety precaution. So for the current issues, we have a mixer up here so that it can evenly distribute the temperature, but due to Navistar's request, they didn't want a mixer on the top so that they can easily access the actual device inside, just in case for swapping out silicone oil or just cleaning up the actual machine. So we are still planning on solving it and just figuring out a solution for that specific request.
Howdy, I'm Eva Barrientos. I am part of the SureFire engineering group as a thermal systems engineer working on the thermocouple test bench. So as part of the key specifications for the thermocouple test bench, one of the major specifications was the operating range ranging from 75 degrees Fahrenheit all the way to 250 degrees Fahrenheit. The thermocouple test bench should be able to perform a sweep between those temperatures and be able to stop at steady state within those at key targeted temperatures. Those may be multiple temperatures ranging within that range of 75 to 250 degrees Fahrenheit, and must be able to hold those temperatures for a prolonged period of time to get more accurate reading at that temperature. The working fluid that was used for the thermocouple test bench actually ended up being a Fluke calibration oil recommended by Fluke for calibration of thermocouples. We are using it in this case because it provides us an even distribution of heat throughout the entire fluid. The power requirement has to be 120 volts. This is just so that it's easily accessible and used. It can be used anywhere along the facility without having a specialized 240 plug or any other proprietary connectors. The thermocouple test bench in itself works as a large automated oil bath being controlled by a watt-low heating system controlled by a Raspberry Pi as well. Those two work in conjunctions to be able to control the heating element as seen right here. The watt-low actually uses a couple of RTD probes that we have installed onto the thermocouple test bench. The ones responsible for detecting thermal gradient in the vertical direction are these two right here, and there are two that go in the same manner as the tested thermocouples that we are testing. The values of the temperature from those thermocouples and RTDs will go to the watt-low, so that the watt-low can reference temperature and determine whether to increase or decrease the wattage going directly to the heating element. The vertical heat gradient will also be dissipated using oil circulation as seen by this motor propeller system here, which will circulate the oil downwards and around in order to be able to get a accurate and identical reading for the 3-inch thermocouples as well as the 12-inch thermocouples.
Hi, so my name is Gabriel Flores. I worked as the fluid systems engineer for the flow transducer test bench, and I worked on the framework as well as some of the engineering analysis. So currently, Navistar does not have any way of testing the flow transducers that they use for everything that they have over there. So since they don't have anything, they just put these sensors to the test and wait to see if they're defective or not. And they'll usually notice this because they usually put in a certain specified flow rate, and then they just don't get any reading or an incorrect reading from the transducer. So we're tasked with building a flow transducer bench which tests out the validity of our transducer test bench, of our transducers. So some of the key specifications that we have for this flow transducer bench is that it has to run anywhere between 2 to 50 gallon per minute. We're also using isopropyl alcohol as the working fluid. This is not only the way that they're going to test the validity of the transducers, but they're also intending to clean these sensors, given that they're also taking these sensors from just the testing site to validate that they're still working properly. another thing is that these flow transducers, they have different diameters. So we're also going to have to work around the fact that because they're different diameter sizes, we have to build different sizes of piping so that it actually, the fluid goes through them. And so to be more specific, the test one that they're using, the one that they're intending to validate, that's going to be referenced with a magnetic flow sensor, which is the one that is actually calibrated and validated, so that we can use that as a reference to make sure that this tested transducer is actually working properly. I know I'm taking too many cuts, but so the frame that we decided to go with was intended to hold all the thrusting forces that will be created from these 90-degree bends. And so originally we had gone with something that resembled like a pegboard, and then we decided to go with vertical beams that would support all this, and also cut down on the material and the machining that these pieces need. And it'll also hold the tank and all the piping around.
Hello, I'm Cyrus Berg, and I'm one of the fluid systems engineers for the Navistar flow rate transducer test bench project. And my role in this project was to come up with CAD models and do some engineering analysis for the flow simulations done on this project. So for the design of the flow rate transducer test bench, our working fluid was isopropyl alcohol for purposes of cleaning, which became one of our major design considerations when selecting a tank and a pump for this project. The tank had to be chemically compatible with isopropyl alcohol, which is why we selected low density polyethylene for the tank. And the pump had to be selected because due to the high vapor pressure of isopropyl alcohol and cavitation issues, which would detrimentally affect the pump and the transducer that would be tested, because it's a turbine style sensor. We had to select a pump that would definitely keep the pressure above that and reduce cavitation to not cause damages internally inside the system. So for the major engineering analysis components, there will be a test sensor up at the top and a master sensor along the vertical side of the pump outlet. The pump will pump directly up through the MagFlow master sensor. The MagFlow master sensor is oriented in a vertical position because that is the optimal position for a MagFlow sensor, and it must have 5 diameters before and 3 diameters after. And the turbine flow sensor is mounted in a horizontal position because that is what is required for a turbine flow sensor flowing a liquid through it. And that must have 10 diameters before and 5 diameters after for fully developed flow to prevent bad readings on the sensor. And we chose a vertical orientation and a horizontal orientation for those two because that would decrease the size of the entire flow bench. And engineering analysis comes in the form of it's using many different size of sensors being tested. A 2-inch diameter sensor is the master, which can read from 2 to 50 gallons per minute, and each of these tested sensors will be varied in size from a 1/2 inch to a 3-inch diameter, which there will be 5 components in the test section that will be needed to change out, and that will be a reducer, a straight section of the diameter of the test sensor, a straight section of the diameter of the test sensor on the outlet, and an expansion to return to the tank. and the engineering analysis came in the form of testing whether or not there would be any, how much pressure loss would be across the reductions and expansions.
And finally, for our closing statement, going forward through summer of 2023 and into fall of 2023 in Senior Design 2, our plan is to continue design work and finalize our designs over the summer and actually begin procurement of materials and hopefully begin manufacturing of the test benches over the summer.